vector equation of a line has four components to it. It will always read r equals, and you should think of r as a coordinate that is representing all of the points on the line. So if a point is on a line, then we can put it into r and it will obey this equation. So that is because r is called a position vector. It means it starts at the origin. You start at the origin and you move x, y, and then z. You're bound to go to the coordinate x, y, z. So it's perfectly okay to think of r as a coordinate. A is also a coordinate. Really, it's a position vector, but think of it as a coordinate of a known point. I know 247 is on this line. It's a fixed point on the line. Lastly, we have D, which is a direction vector. And this is any vector at all, anywhere in space. It doesn't need to start at the origin. It doesn't need to even be on the line. We just need to know that it's pointing in the same direction as the line. And then the traditional letter is lambda, but you will often see T or S. It doesn't matter. And this is a scalar constant that represents a unique number for every position on the line. So, for example, S is equal to 0 is 247. S is equal to 1 is 4, 5, 10. S is equal to 0.1 is 2.2, 4.1, 7.3. These are all points on the line because they all obey this equation. So this is what's going on in 3D. You should think of lines as not particularly perpendicular to anything. They're infinitely thin. It's very hard to draw them on paper. If you keep a diagram in 3D moving, you can sort of understand it better. So there's that fixed point A. That's just one of the points on the line. I've drawn D as this grey vector here. It's parallel to the line, and that's the only feature it needs to have, a vector that is parallel to the line. The idea is we can start at the origin, we can travel from the origin to A, and that means we've got ourselves onto the line, and then we move as many D's as we like. So I could move this D along here and travel along the line as many times backwards or forwards as I like. So let's run through a few techniques. First of all, is a point on a line? So to determine this, I'm going to show you a couple of different ways of thinking about a line. Here is the equation of the line. I've rewritten R as x, y, z. And if 459 is on the line, then R must be able to represent it. However, I'm going to make it a bit clearer by writing the vector equation in parametric form or as a coordinate. All of these three things are absolutely identical, and you use whichever format you prefer for each question. Parametric is often the easiest one. It's really clear. Let's try answering the question in this one. So is there a value of lambda that works? Well, I can see straight away from the top equation lambda is equal to 1. Yep, that works for the second equation. Good so far. But it doesn't work for the third equation. So this shows that 459 is not on the line. Perhaps we didn't need to go into parametric form. We could have just seen it here, because you can do it in your head. 4 is equal to 2 plus 2 lambda. 9 is equal to 7 plus 3 lambda. We can also think of it as a coordinate. Is there a value for lambda that could hit this coordinate? So these three ways of thinking of a line are really important. So a few techniques involving two lines. Let's show they're not at right angles. This just speaks to two things. One is, the second you see right angles, you should be saying, right, a dot product is equal to 0. I need to show that. Or in this case, not at right angles, I need to show a dot product is not equal to 0. That's how you prove things are or are not at right angles. And then it's just, do you understand what the equation of a line is? And which two vectors are we going to dot product? And it's going to be the direction vectors. It's irrelevant that 247 happens to be on the line. What's important about right angles is what direction the lines are pointing in. So I dot product them, 2, 1, 9, added up, and you get 12. That is proof they are not at right angles. What is the angle between these two lines? Well, we have a formula for the angle between two vectors. So which two vectors are we going to put into this formula? Well, obviously the two directions again. So just put them into this formula. Sorted. Intersection of two lines. We're basically going to put them equal to each other. And then say, I need all three components to work. So I'm going to look at the top two components first. I've told the examiner what I'm doing. It also helps me think. I'm saying the x component or coordinate must be the same if these two lines are going to intersect each other. The y component must be the same. If they're both the same, I can now solve these and I get this. And then I test the z component. There's the z component. I put in 1 and 3, and sure enough, 7 plus 2 is 1 plus 9. The z component also works for this combination of lambda and mu, and so the lines do intersect. If this z component had been different, we would have said they are skew, and we must remember to actually write the answer down, which is putting lambda into here. That gives me 4, 5, 10. And I would also double check to make sure I've done it right by putting mu into the other one. That is 4, 5, 10. Now, lovely. Another video will show you how lines and planes